Hello everyone, I'm Manos. I work at Linaro and the virtualization and emulation team. And in this talk, I'll try to talk about why you should care about Rust in QEMU and what particulars you should pay attention to instead of being strictly an introduction to Rust. Like I want to appeal to people both familiar and unfamiliar with the Rust language. And I will provide information and hyperlinks that you can check later. So you can check the slides PDF if you like for reference. Okay, so let's see the current state of things from a bird's eye view. Rust in QEMU is currently experimental. It was released in 2014. It's disabled by default because you require a Rust compiler to build it. We cannot require the Rust compiler just like we do C and Python right now. So the problem with this is that we cannot use Rust for core QEMU internal implementation. Instead, we can write devices, and that's what the first thing we did was write a new device. And it's possible to have Rust-only devices, but so far we only have ones with C equivalents. So you can switch between the C implementation and the Rust implementation. It's not necessary though. It's just so that it's very rare to have to need to add a new device in QEMU. Like usually you just maintain stuff and improve things. Besides devices, at this stage, I think that TCG plugins could also benefit, but that would require writing bindings for TCG, and we don't have that currently. So remaining challenges, like mentioned in the previous talk, Mason support is pretty good, I think. There's still some improvements, but most QEMU developers probably don't have to deal with the build system itself. We need to ship new code because it's a chicken and egg problem. Like if no one starts writing code, no one will ever do. So we need to overcome the initial inertia. And something more pragmatic, it's that Rust has showed up in slowly moving distros like Debian only recently. That's because they're very slow, and also the upstream Rust project moves very fast, which is incompatible with this kind of distro release schedule. And a lot of recent Rust language improvements have arrived after the Rust in Linux project gained momentum. And many language features in general have been years in the making. And QEMU, though, is fortunate that we do not need low-level features useful for kernel programming, because it's not that low level, right? But we really benefit from stuff like compile time evaluation and better C interoperability. So generally, we would like as new version of Rust as possible. And here's a quote from Nico Matsakis, who's a core Rust developer and a fellow Greek. He says that his vision for Rust is to be able to use it to build all kinds of software from CLI to development tools, but also embedded microcontrollers or even kernels like Linux and Windows which use Rust today. So let's look at the strengths and opportunities of having Rust in QEMU. First, probably the most well-known fact that you're already familiar with is that there's no garbage collector. You already know that, probably. Instead, we have a static compile time analysis that detects when a value is not alive anymore and inserts destructor calls automatically. Additionally, it has move semantics. Reference can be mutable or immutable, which allows for aliasing to exist for more than one mutable reference to exist. But that's not all, though. Many C problems simply get eliminated. Like we have bounce checking when you access an array. We don't have integer promotion or truncation. You have to explicitly cast and convert things. There's no undefined behavior by default, which is very important. And I say by default because if you want it, you can get it. You cannot ignore error values by default, like, for example, the result type that was mentioned in the previous talk. The compiler would complain if you try to do that. And that pretty much eliminated most of C bugs that people deal with. Of course, that leaves us with a big amount of, with a big percentage of bugs which is logic bugs, which you can't really escape easily. You can get that with many other languages, I think. Like even garbage collecting memory safe languages would be ideal. So the problem is we also want to interface with C. And Rust has full support for both calling and defining C-like functions, as well as defining structs with C in memory representation. So you can have compatibility with the C side of QEMU and the Rust side. And of course, very important, in most cases the code you will write will not require many compile and rewrite cycles just to make sure it doesn't segfault. However, does that mean that you cannot shoot yourself in the foot like you can with C? Of course not. It requires extra steps. So this code is from the Rustonomicon book, which is a very interesting official documentation about the unsafe uses of Rust with FFI interfaces and other low-level stuff you might be interested to do, which I recommend to read. It's a good read. So it says that Rust is a safe programming language, but it's also unsafe because it allows you to choose whatever flavor you want. So memory safety is the selling point of this language, but it's not the complete picture as far as safety is concerned in general. So to understand that, we have to see what safe means actually for the Rust language. So there is an unsafe keyword that you can annotate function signatures, traits, or code blocks, scope basically. That means that if something can put your program in a bad state, even if it doesn't, for example, dereference invalid memory, you can choose to put it behind unsafe. And anything that the compiler, the borrow checker, or the type checker cannot prove statically is eligible for being annotated with unsafe. So like it's up to you, the programmer, to make that choice. And essentially, Rust is two languages, right? And your QEMU code does not have to be entirely unsafe. You can split your implementation to distinct safe and unsafe parts, and you should strive to make that distinction always. Note, however, that you cannot turn the borrow checker off. You can only override it by creating raw memory references or pointers, and then dereference them in unsafe blocks. So it's always a conscious choice to get around the safety mechanics of Rust. So basically, you cannot perform anything unsafe without wrapping your code in an unsafe code block. This is a contrived example. So basically, we just create an integer variable, a raw mutable pointer to it, and then we wrap it with a non-null type that guarantees that the raw pointer inside it is not null. And because we use the unchecked variant of the constructor, we have to promise to the compiler that it's not null. So what we can see from this example is that the code that's inside an unsafe block doesn't have to actually be unsafe. It just means that it's potentially unsafe. So there's a big difference. And the advantage of the split is that every unsafe use in the code base and the patches we send in the mailing list can be individually inspected during code review, because it makes it very easy to know which parts of your code can potentially trigger logic bugs or undefined behavior. The truth is that, similar to Rust in the Linux kernel, things do not perfectly match with C, because we still have code in C, right, that uses different kinds of memory management. And also concurrency primitives like mutexes that are not compatible. So, like the borrow checker cannot attribute a lifetime to allocations that come from C or from anywhere else. So we can still do that for internal Rust allocations. But for QEMU stuff, we have to delegate the management to QEMU, like we do in C. We also cannot check for memory aliasing, which is also pretty bad. That's because we don't have a borrow checker, yeah. So the solution is to use interior mutability with bindings and wrapper types, like mentioned in the previous talk. Okay, so how to add a new device? It's very straightforward. You can look at the existing devices and copy the structure. So, like, because of Meson limitations, we put all Rust code in the Rust directory, but we mimic the same directory hierarchy for subsystems. We then compile each device as a standalone library, and then we link it to the rest of QEMU. And note that, in contrast with C, a library is a single compile unit. It's not like in C where you compile its .c file into an object. Okay, this is a rough example of what your Mason.build field should look like. Things change frequently, so for a more up-to-date view, you should always see what's upstream and what other devices do. You don't have to read that, that's just for reference. Okay, let's talk about how we have access to C bindings at all. So we use a tool called bindgen to convert C headers into Rust equivalent definitions. And bindgen declares them as extern, like in C++. This is done automatically by the tool, and in 99% of cases you won't need to interact with it. Only if you need to add missing bindings. So to add new code, you just include it in the C header file, or files, plural, that we pass as input to bindgen. Currently in upstream QEMU, we have a wrapper.h file, which is the input that you have to modify to add new stuff. But even if you have to do that, it's really simple. You just add a line, and you can see an example of what the generated code looks like. And there are some knobs and toggles you can use to adjust output for some types, like enumerations. But like I said, you probably won't need to deal with that. So there are two ways Rust code interacts with C parts of QEMU, just like in the kernel. It calls into existing C APIs, and QEMU C side can also invoke Rust code when it initializes stuff, or it calls a callback. And you can define functions with the extensc API very easily. And the problem is that calling other QEMU C functions will necessarily make you use the unsafe keyword. So it's best to write safe bindings for those calls so that other consumers of those same functions do not have to duplicate instances of unsafe use. And if you're unsure, feel free to ask for feedback in the mailing list. Okay, so in general, you should avoid using raw pointers. You should use wrapper types that we have in QEMU, like opaque, and like non-null that we saw earlier, which is from the standard library. And you should always use mutability if you know that your C reference objects can be accessed safely. For example, because no one else in the QEMU site has a reference to it, or because you hold a lock like the big QEMU lock. You should definitely try to reduce instances of unsafe, like as previously stated. And we should use static checks for things like state machines or the builder pattern type as much as possible, because that catches a lot of errors. And finally, for things like type or module initializers, etc., it's best to use macros because we don't want to repeat ourselves with such boilerplate. So how to write a safe wrapper? So this was the point of the previous talk, and I think that writing the safe wrapper is more about exposing idiomatic Rust to the consumer of your API. And there's no single answer as to what idiomatic Rust is, right? Here are some rough guidelines you can have for reference. I also recommend looking at source code of individual Rust standard library types that you use and functions that you use, because if you go to generated Rust documentation, it's very easy to go to the source of that documented item. You just have to click the source link. Your device might also need to use external Rust dependencies, most probably. It's very easy for the number of dependencies to blow up. I personally prefer not to add dependencies when I have to, because it makes me nervous to see hundreds of dependencies being downloaded, and you know that you cannot inspect and review them all. We do need dependencies though, so like in that case we should follow existing documentation and recommendations that we have in our developer section. So what parts of Rust, as far as ergonomics go, are the most useful to QEMU? And we're talking about ergonomics and not just types, safety, or other kinds of static checks. I think that macros are very important for QEMU because a project, a code base with object-oriented programming interfaces needs a lot of boilerplate that it's very hard to get wrong. And we get away with it by defining preprocessor macros in C. But we can get away with more with Rust macros because they're more powerful and safer. In Rust, there are two kinds of macros. There's a declarative and procedural macro. And the declarative kind is expanded while your code is compiling, whereas procedural macros require a separate code gen stage during compilation. And they are akin to compiler plugins, basically. Currently, we put those in the QEMU-API-macros create library. So the declarative kind is the simpler of the two, and you can define them anywhere, like with preprocessor C macros. They have more control over how parameters expand. So in this example, QM is a declarative macro that just implements a trait that allows you to interpret dummy state, which is an object, as another kind of type very easily. And you can do that through the type system. And we also have procedural macros, which are more complicated, but you're unlikely to need to write one. However, you are going to have to use them. So you should know how they work. So basically, they receive a list of tokens and they output tokens, meaning syntax tokens. And if the output fails to compile, you will receive a compilation error. Here in this example, object is a derive macro, and I think currently it just registers the type with QEMU. I'm not sure if, I don't remember if it does anything more than that. But in order for it to work, dummy state has to implement the object implementation trait. So if you have neglected to do that, this will not compile. In case you're interested to learn how to write procedural macros, I have included 2 links that you can refer to. Okay, finally, I sat around trying to think some potential future work ideas to suggest for people who might be interested. So this list is non-exhaustive. Personally, I would like to see safe QEMU internals, because a memory-safe language is good for stuff that handles a lot of input and untrusted data, like parsing, for example, or making lots of allocations and serializing data like QAPI. TCG plugins, like I mentioned, I think they could become more powerful because they could gain a higher kind of abstraction and safety. And finally, we can also use async code. It would require a significant effort, I think, to port QEMU's event loop to support that, but it can be done incrementally. And I think that eventually C code could run async, but it would be transparent to it that it could also run aside Rust, even if we replace the event loop with a Rust implementation to support Rust. Some other suggestions: it would be nice to have custom static analysis for QEMU specific stuff. Like, for example, we can check that things are only accessed when the BQL lock is held. Lastly, it would be very nice to use existing Rust virtualization projects like VirtIO FSD and Rust VMM libraries. Rust VMM has mostly VirtIO specific library crates, but not exclusively. There are generic stuff that VMMs can use, like the VM memory library, which can abstract access to the guest memory space. I would like to thank every QEMU contributor. I have included some links to community places you can check if you're interested. The wiki page, the mailing list, and an IRC channel that we have, an OFTC that's in parallel with the QEMU IRC channel. And thank you for your attention. Do you have any questions? Thank you.